In this video, we're going to talk about calculating the pH of a weak base. So, a typical question you may see is, what is the pH of 0.1 mole per liter solution of ammonia? So, ammonia, we can look up. We should just know this one though, is NH3 aqueous. So that's a weak base. We're going to find it on our acid-base table. It's the conjugate base of ammonium, which is NH4+. And ammonium, NH4+, has a Ka value of 5.6 times 10 to the negative 10. And we're going to need that to calculate our Kb value. So we're going to start this as we normally would. We're going to write down our reaction with water. So ammonia reacts with water. So ammonia is a base, so it's going to be a proton acceptor. So it's going to form NH4 plus OH minus. So we're going to just do our ICE table as per usual. So ICE down the side. The initial concentration of ammonia is 0.10 moles per liter. We never include water in our acid-base calculations, and we don't have any of the products to start. So we're going to represent our change with the letter X. So we're going to use up ammonia and produce ammonium and hydroxide at a 1:1 mole ratio. So our concentration at equilibrium will be 0.1 minus X, and then X and X. So at this point, we can set up our Kb expression. So Kb, our base ionization constant, is going to be our products. So NH4 plus times hydroxide divided by the concentration of ammonia. And again, we don't include water. Now we need to calculate Kb. Kb is not in our table. We have Ka instead. So first thing we're going to do is calculate Kb. And we calculate Kb by dividing Kw by the Ka value of its conjugate acid. So that's why we need to know the Ka value of ammonium. So Kw is 1.0 times 10 to the negative 14. Ka here is 5.6 times 10 to the negative 10. And our Kb value is 1.8 times 10 to the negative 5. So we can plug that into our expression. We can plug in all of our numbers that we have. So we have 1.8 times 10 to the minus 5 equals x squared, because they're both x's, divided by 0.10 minus x. Now, this would lead us to the quadratic formula, which is not something that we want. So we're going to test, can we get rid of the x value here? So we're going to do our approximation. So we're going to say 0.10, our initial concentration of our base, divided by the Kb value, which is 1.8 times 10 to the negative 5. If that's greater than 1,000, which it is, that tells us that we can say that 0.10 minus x is approximately equal to 0.10. So what we're saying with this assumption is that the percent ionization of ammonia is very low, so x is negligible, meaning it won't significantly change the concentration. Negligible. And so we can just ignore it to make our life a little bit easier with the math. Okay, so I'm just going to move this up a little bit. All right, so we can rewrite this as 1.8 times 10 to the negative 5 equals x squared over 0.10. We can solve for x. It's going to be the square root 0.10 times 1.8 times 10 to the negative 5. And we get that x is equal to 1.3 times 10 to the negative 3 moles per liter. This is the concentration of hydroxide. So we can use that to find our pH, though not directly. So we have a concentration of hydroxide. We need to find pH. So we have two options here. We can go from the concentration of hydroxide to the concentration of hydronium using Kw to pH. We can go from the concentration of hydroxide to POH to pH. Either pathway will get you the same answer. I'm going to use this pathway. So I'm going to find first POH is going to equal negative log the concentration of hydroxide. So negative log of 0.1, of 1.3 times 10 to the minus 3 moles per liter. And I get 2.87. So I get 2 sig digs, because I had 2 sig digs in my answer originally. And then pH, we're going to assume this is at 25 degrees. So 14 minus our POH. And we get 11.13.